Free body diagrams. A free body diagram is a visual representation of force and object interactions in which individual objects or members are isolated from their environment or system, illustrating all external forces acting upon them. For the example, we would isolate the lady from her environment to see the forces that will be acting upon her. And a force is a straight line push or pull acting upon an object, and you can see that there is a force of gravity pushing down on the lady, allowing her to stand, and there's an applied force, which is her weight pushing on the ground. And moment is a twisting effort about a point of axis when a force is applied at a distance, and the formula for moment is force times distance. Moments. The moment of a force is a measure of the tendency of a force to rotate the body upon which it acts, and the unit should always be pound to feet, and the distance must always be perpendicular to the force in order for you to use the formula, and clockwise is negative and counterclockwise is positive. So for the example, you would first have the formula, which is moments equal force times distance. Then you need to convert the distance, the inches, into feet, and 12 inches equal 1 feet. And then you can see that the force acting upon the wrench is turning clockwise, which make the force negative, so negative 90 times 1, and the moment equal negative 90.
Deflection and about the moments of rest. Moment of inertia. Then you need this to calculate the relative velocity and the deflection. Moment of inertia formula is t times v multiplied by third, all divided by 2. Moments of elasticity is a ratio of increment of some specified velocity to the increment of some specified strength, also known as the coefficient of elasticity, velocity modulus. Elastic modulus is defined as the stiffness of an object related to material chemical properties, and E is equal to stress over strain. There is a simpler version of that definition that was a paragraph long. The beam deflection formula is F times L to the third divided by 48, the modulus of elasticity, which is known as E, times the moment of inertia, which is I. So it is very important that we know the base and the height, and we calculate the moment of inertia first, and then do the rest, so it is easy for a person to do it. And a lot of the rest is usually given in that circumstances because we are not able to memorize everything. And now we are going to practice what the practice problem is showing you to correct. Now find the beam deflection if there is a 20-pound force applied to the beam. So basically, we want to know how much it's going to go down, like how much it's going to deflect. And in order to do that, we'll just use a simple formula of the beam deflection formula. And we're just going to plug in numbers. So the base is 2, and the height is 16, and the pound is 20. So we calculate, now let's try calculating the moment of inertia, which is base 2 times height 16 to the third, and that would give you 4096, and that's the moment of inertia. And then just plug that in, and we are giving you E. And we just found a online for a standard beam, and we just gave that in. So it's just a standard beam. And then just plug in the pounds and plug in everything else, and you get 0.166666. So that's it. Calculating those numbers factors. Trigonometry is very important. So here we see our characters time is all together. So we have F So here, sine, cosine, and tan are very important. So sine is opposite over hypotenuse. Is cosine is over tangent. Is tangent, which is opposite over adjacent. In this case, we use that situation. As you can see, there is a vector, and there are two vectors that can be 3 and 1 vector to the right, and 10 units. And we are going to try to find the magnitude of the other vector. So how we can find these because we have x. So oops, 30 degrees using the formula of in this case, we don't necessarily need to use the knowledge of having just a right triangle because this is a force vector. We are not so what we do all of our operating functions is limited by the magnitude of x is
Okay. Okay, now on to centroids. Centroids are basically the balancing point of a shape. So looking at the side, currently we got a square, we got a triangle, and we got a circle. So for finding the centroid of a square, you take the length divided by 2, and you take the height divided by 2. So once you get to numbers, you use the bottom left corner as your origin. This is very important since it tells you where the centroid is located on the whole shape. So for the square, the centroid is located at 1, 1, 1, 1. Okay, so now moving into the triangles, it is the same concept. The origin is located at the bottom left corner, except now for the x and y coordinates, you divide them by 3. So what you do is here is for the length you divide it by 3, the height you divide it by 3 using the bottom left corner as the origin. You get that the centroid is at 2 divided by 3 comma 2 divided by 3. Now for the circle, what you want to do is a little bit different. The x coordinate will be your radius and your origin will be the center of the circle. For the y coordinates of the centroid, you just simply take the radius divided by pi and multiply it by 4/3. Okay, now moving on to more complex shapes. When you see a complex shape and it's asking you to find the centroid, simply divide the shape into more simpler shapes as shown here. The larger rectangle is the larger L shape is divided into a square and a rectangle. So right here we have the square, which is portrayed as 1, which is portrayed as 2, and the rectangle, which is portrayed as 1. Okay, so now we just need to start filling in this chart. You need to find the area of both. So the area of square 2 is 2 divided by 2 is 2 times 2, which is 4. You can now fill in this box right here and this box right here. Now the area of rectangle 1 would be 2 multiplied by 6, which is 12. Now you can figure out 12 and you add them into the chart. Now we need to find the centroid of both of these shapes. Both of these shapes, what you want to do is first identify your origin, which is going to be the bottom left corner once again. And so finding out the centroid for shape 1's x coordinate is 3, simply 6 divided by 2. Now the centroid for shape 2, what you want to do is 2 divided by 2, which is 1. Now you fill in 3 and 1 correspondingly. Now for the y coordinates of both of these centroids, what you want to do is once again the exact same thing, which now you get 1 and 3 for the coordinates of the centroids of both. Now, once you have filled in the second and third columns of these two charts, what you want to do is multiply the area of each shape to the corresponding x or y coordinates. Now you can get your fourth column, which is 12 times 3 equals 36, 4 times 1 equals 4, 12 times 1 equals 12, 4 times 3 equals 12. Now you can get your fourth column. Now moving on to your penultimate step, what you want to do here is you simply want to add these two numbers, the totals of the multiplied area and the coordinates, right? So now you add 36 and 4, get 40, as shown right here. 12 and 12, get 24, which is shown right here. Now divide both of those numbers by the total area of the whole shape, which is 16 in this case, since 12 plus 4 equals 16. Once you get these two numbers, 2.5 and 1.5, those are correspondingly your x and y coordinates for the whole shape, or the centroid.
Here's a basic truss video, or truss problem. Here's your fixed pin. Here's your roller pin. Here's your external force. So to start off, you're going to have to convert these pins into forces. So the fixed pin has two external forces, and the roller pin has one external force. So to find these unknown external forces, you're going to have to do the method of moments. So as you can see here, you have that 10 external force, and you have these 3 external forces that you don't know. So we're going to establish a joint right here, and we're going to imagine that this member is turning this joint clockwise, and this long member right here is turning this joint in an unknown direction. So we're going to use the moment formula. So it's going to be 10, which is a force, times 3, the distance from the point, which is d, equals
Why is there a diagram of a circle?
Unknown force times 6, which is the distance, plus 3. So if you solve for f unknown for 12, you're going to get equals 5. So you can just fill that in right there. And since this force was essentially turning this joint clockwise, you can assume that this force is going to turn this joint counterclockwise. So it's going to be, think of it as a clock. And since the external force is only 10 newtons down, you can assume that this horizontal force is 0, because the truss has to stay at rest during the problem. So you can just write 0 right there. So now that you have the y forces left to do, you can see that there's only one down force, below 10, and 2 up forces, 1 over 8 and 5. So you can just do simple math right there. 10 minus 5 equals 5. And this one's going to face up also to counter down force. And that's how you finish off the external forces. Now for the internal forces. So when you're doing internal forces, you're going to calculate the compression force or tension force inside a member, such as the Milo. So when you're dealing with these members, you're going to look at the forces surrounding it or nearby. So you're going to see this 5 newtons going up, and that's about it for the forces around this line. So you're going to draw a triangle. This right triangle is used to represent the up and down forces of this joint, this member, because it's going to have x and y coordinates. So you can just imagine unknown y and unknown x. So you can have the member right here, force the member. And since then, so basically redraw this half of the truss right here. You're going to have unknown internal force right here. So unknown internal force right here. And upward 5 newtons. And you're going to have theta to represent the angle. And you're going to label the distance. And you're going to label the unknown force as longitudinal. So and you're going to, basically you're going to set the x components, you're going to set the y components of this unknown force. So F sine theta. You use the trigonometric formulas when you're calculating the internal forces. F sine theta is phi, because you want the y component of this force, of the internal force, to cancel out 5 newtons going on. And to solve this problem, you're going to have to find theta, which is the angle. So to do that, you can just do inverse tan opposite over adjacent, which is going to be 4 over 3. And once you found theta, you're just going to solve for the unknown force. So 5 divided by sine 53.13 is equal to about 6.25. So you're going to label this 6.25. And from there you can find out the horizontal internal force of this member, which is going to be 6.25 sine 53.1, which is the cosine. Think of sine as the y forces and cosine as the x forces when you're doing internal forces. That's going to equal that's going to equal 3.75. So you can just label this part 3.75 as the internal force. And since the external force on this point is 5 newtons up, and the force within this joint is 6.25, and the force right here is going to be 3.75, then the y component of this member is going to be downwards. So you can tell that it's going to be down and left. Since it's going to be down and left, the horizontal component of this is going to be the right to counter the left x component of this member right here. So if you go back to the main diagram, which is pretty messy, you can label this 3.75 going that way. 3.75 going that way, because